It's just wild when you think about it. For almost all of human history, the question, are we alone, was, pure philosophy.
Purely philosophical, yeah.
But there's a date. Before 1992, we had 0 confirmed planets outside our solar system. Not a single one. Now, we've cataloged thousands.
And that catalog has, well, it's basically broken our old models of the universe. We used to think every solar system would look like ours.
The Copernican idea, right? We're not special, so everyone else should have small, rocky planets on the inside, big gas giants out on the edge.
Exactly. And the data just threw that assumption right out the window.
Yeah.
We are finding worlds that, according to the old textbooks, just shouldn't exist.
Okay, but before we get to the cosmic freak show...
And it is a freak show.
We have to talk about how we're finding them. Because we're not really seeing them, are we? I mean, they're millions of times fainter than their star.
Right. Direct imaging is incredibly rare. Almost everything we find is through indirect methods. The main one is the transit method.
That's where missions like Kepler and TESS just stare at stars and wait for a little dip in the brightness.
A tiny dip. It means a planet has passed in front.
But there's a huge selection bias there, isn't there? You're only going to catch planets that are perfectly lined up with us.
That's the catch, yeah. It favors big planets on fast orbits. They make a bigger dip, and they do it more often.
So how do you get around that?
We pair it with another method. Radial velocity, we call it the wobble method.
Okay.
Instead of looking for a shadow, we look at the star's light. A planet's gravity actually tugs on its star, making it wobble back and forth.
And that wobble changes the light.
It stretches and compresses the light waves, the Doppler shift. And the precision is just staggering. We can detect a star moving at the speed of a person walking from light years away.
Wow. And that gives you the mass?
It gives you mass. The transit gives you size, you put them together, you get density, and that's when you know if you're looking at a rock, an ice giant, or a ball of gas.
And that's where the weird stuff starts? The hot Jupiters.
Oh yeah, the first things we found. Gas giants orbiting their stars in, like, a few days. They are so close.
Which shouldn't happen, right? The model said gas giants had to form way out in the cold.
It totally wrecked the old models.
Yeah.
It forced us to realize solar systems are violent, dynamic places. These giants probably formed far out and then spiraled inwards, just bulldozing everything in their path.
And then there are the super Earths.
The most common type of planet in the galaxy, it seems. Bigger than Earth, smaller than Neptune.
We don't have one. Our solar system is missing the most common type of planet out there.
Which is the biggest hint that maybe we're the outliers. But, everyone always wants to talk about habitability, the Goldilocks zone.
Not too hot, not too cold, just right for liquid water, but that feels way too simple.
It is too simple. A planet like Proxima Centauri b, our closest neighbor, is in the habitable zone, but it orbits a red dwarf.
And those stars are nasty. They have these violent flares.
Constant violent flares. They can blast a planet with X-rays, strip away its atmosphere. So you can be in the perfect temperature zone, but you're just a sterilized rock. It's not habitable at all.
So we need to look closer, which is where James Webb comes in. We're moving from just finding planets to actually characterizing them.
We're going from stamp collecting to, reading the atmosphere of these worlds.
Through transmission spectroscopy. I love this idea.
You're basically watching starlight as it filters through a planet's atmosphere. The chemicals in the air absorb certain colors of light.
So by seeing what colors are missing, we can tell what the air is made of.
Exactly. We can sniff the air of a planet 100 light years away, looking for biosignatures. Oxygen, methane, water vapor, signs of life.
It's just mind-blowing. It puts everything into perspective. We're searching for a second Earth, but the more we find, the more it seems like our Earth is pretty specific.
It really is.
And that brings us to a final thought for you to chew on. Super Earths are common. Hot Jupiters are common. Systems around red dwarfs are the most common. But a system like ours, a quiet yellow star, a neat little arrangement of rocky and gassy planets.
Statistically, that seems to be pretty rare.
We spent all this time assuming we were the blueprint, the boring average model.
But the data is starting to paint a very different picture. What if we're the cosmic weirdos?
So we tend to look at our own solar system, think, this is the standard, everything is stable, everything has its place.
It feels like the default setting.
Right. But we've got this exoplanet evolution report in front of us, and it paints a much more chaotic picture. It suggests our stability is actually the exception.
It really reframes the whole field. Planetary science becomes a study of survivorship. We're not just looking at planets, we're looking at the few that somehow made it through a cosmic gauntlet.
A gauntlet. I like that. So let's trace that journey. Let's start at the beginning. Phase 1, the birth. We're talking 0 to about 100 million years.
We're in the protoplanetary disk. And the report highlights two very different ways things can go. Core accretion or gravitational instability.
Okay, so core accretion is the slow build, right?
Yeah, that's the slow path. Dust sticks together, makes pebbles, then boulders, and on until you have a core big enough to pull in gas.
And the other one, gravitational instability.
That's the fast, chaotic option. A whole massive chunk of the disk just collapses under its own gravity. Boom, you have a gas giant, formed very, very quickly.
And central to all this is the snow line.
Absolutely crucial.
Yeah.
It's just the distance from the star where things like water freeze. If you form outside it, you can build up ice and become a giant. Inside, you're more likely to be a rock, like Earth.
But the report makes it super clear where you form is not where you necessarily stay.
Not even close. This is the era of migration. The gas in the disk actually creates drag. It steals orbital energy, and the planets, they spiral inward.
Which explains hot Jupiters, these massive planets orbiting closer than Mercury.
Exactly. They didn't form there. They fell there.
And it's not just falling. There's this thing called the grand tack, which sounds like orbital billiards.
It is. It's a gravitational tug-of-war. Planets push each other around. Sometimes one gets flung into a wild orbit, and sometimes
It gets ejected completely.
kicked out of the system, becomes a rogue planet just drifting alone in the dark.
Okay, so let's say you survive that. You don't fall into your sun, you don't get ejected, you make it to the teenage years.
Now the real battle begins. The report calls it atmospheric sculpting. It's the planet versus its own star.
And the star is the antagonist here.
A very aggressive one. Young stars blast out a ton of X-ray and UV radiation, what we call XUV.
And that radiation just strips atmospheres away.
It can, yeah. It heats up any hydrogen atmosphere until the gas just escapes the planet's gravity. It's called photoevaporation.
This must be why we see that radius valley in the exoplanet data.
That's the leading theory. We see small rocky planets and we see bigger mini Neptunes, but almost nothing in between.
Because you can't stay that size.
Right. Either the star strips your atmosphere and you shrink to a rocky core, or you hold on to it and stay big. There's no middle ground.
But the planet can fight back. It can make a new atmosphere, a secondary one.
Throughout gassing, yeah.
Yeah.
Volcanoes spewing out carbon dioxide, water vapor. But it only works if you have a shield.
A magnetic field.
The magnetic field is everything. If the planet's core cools and the dynamo dies, that shield goes down. The solar wind just scours the new atmosphere away. Game over. You get Mars.
So assuming you survive all that, what about the end game? The star starts to run out of fuel.
It enters the red giant phase. And for the inner planets, this is almost always fatal. The star just swells up.
And swallows them whole.
Engulfed and vaporized.
Yeah.
Mercury, Venus, Earth. In that scenario, they're gone.
What about the outer planets?
They have the opposite problem. As the star loses mass, its gravity gets weaker. Their orbits expand. They drift away into the cold.
Until the star collapses into a white dwarf.
And that's the final twist. The white dwarf is tiny, but it's super dense. So surviving planets can get their orbits destabilized all over again.
This is where we get the term planetary pollution, right?
A grim term, yeah. We literally see the elements of rock iron, silicon polluting the atmospheres of white dwarfs.
It's the debris of a shredded planet raining down on its star's core.
That's what it is.
It just makes you realize that a planet like ours, a living planet, is such an anomaly. We're the result of this 4 billion year balancing act that somehow just kept working.
Completely. You have to survive the migration, fight off the star's radiation, keep your core hot enough for a shield, and do all that before the star itself decides to swallow you.
It makes Earth-like feel less like a category and more like a momentary pause in an incredibly violent process. So here's something to think about until the next deep dive.
Okay.
If the window for a stable living planet is that narrow, are we alone in the universe simply because we're one of the very few currently in the safe part of our star's life?
That is a heavy question.
Thanks for listening to this deep dive. Stay curious.
So here we are. It's early February 2026. And if you follow the mission manifests, you know this is.
Yeah.
This is a huge moment. The immediate fleet launch window is now open.
It really is. We're on the cusp of a fundamental shift. We're moving past just, finding exoplanets.
Right.
Between now and 2030, the whole game changes to characterization. We're not just counting them anymore. We're going to be reading their air.
Looking for biosignatures,
Yeah.
maybe even, industrial pollution?
Potentially, yes. It's all based on this roadmap from ETHE and NASA. We've got Plato, the Roman telescope, and Ariel all getting ready to go.
And it all kicks off with Plato later this year. This one feels different from TESS, doesn't it? It's not just scanning the whole sky.
It's a targeted hunt. Plato is designed to do one thing exceptionally well: stare at sun-like stars for a long time to find rocky planets in that Goldilocks zone.
The Earth 2.0 candidates.
Those are the ones. Plato is the scout. It finds the prime targets for everyone else.
Yeah.
And once it does, that's when the Roman space telescope comes in, around 2027.
The tech on Roman the coronagraph instrument, the CGI, that's a serious piece of kit.
It's a game changer. It's basically a hyper-advanced star shade inside the telescope. It physically blocks the star's glare so you can see the faint little planet right next to it.
So you can directly image these worlds.
The giant ones, yes. But Roman also has another trick: gravitational microlensing.
Which uses gravity itself as a lens, right?
Exactly. A star passes in front of a more distant one, and its gravity magnifies the light, revealing any planets orbiting it that we would have completely missed otherwise.
Okay, so Plato finds the nearby candidates, Roman images the big ones and finds the distant ones, and then Ariel launches in 2029 to, do the chemistry.
That's the synergy. Ariel is the census taker. Its job is to stare at about 1,000 known planets and just read their atmospheric barcodes.
And the barcode we're all hoping to find is still that oxygen and methane combination, I assume.
That's the classic biosignature, yes. Because they shouldn't exist together. They cancel each other out chemically, so if you see them both...
Something has to be actively producing them. Like life.
Precisely. It's a state of chemical disequilibrium that screams biology.
But we're also looking for something less natural. Technosignatures.
Right. We're actually hunting for alien smog, things like CFCs, chlorofluorocarbon.
Industrial pollutants.
If you find CFCs in an atmosphere, that's not life. That's a factory. That's a civilization.
It's so interesting that we're looking for signs of industry, of heat, but then just this year we got confirmation of HD 137010b, cold Earth.
A crucial discovery. It's on the far cold edge of its habitable zone. And the theory is that a really thick, hydrogen-rich atmosphere could act like a planetary greenhouse.
Trapping enough heat for liquid water.
So it just expands our definition of habitable, which, makes the job of the next flagship mission even more important.
The Habitable Worlds Observatory, the HWO, for the 2040s.
That's the end game for this whole roadmap. The goal is to directly image 25 Earth-like planets. And to do that, you need to suppress the starlight by a factor of 1 part in 10 billion.
10 billion. That's the old analogy, isn't it? A firefly hovering next to a giant searchlight.
And you're trying to spot the firefly from hundreds of miles away. But if HWO can do that, we're not just detecting a planet, we're analyzing its air.
And if we find that air, the breathable air, the next question is obvious. Can we go? Which sounds like fantasy, but people are working on it.
They are. The breakthrough starshot concept is, theoretically, sound. You use powerful lasers from Earth to push these tiny gram-scale light sails.
Push them up to, 20% the speed of light?
Something like that. At that speed, you could get a probe to Proxima Centauri in about 20 years.
And that's the thing that gets me. 20 years. That's a human lifetime. We could launch it and, still be here to see what it finds.
Think about the timeline. We've gone from asking, are there other planets, to, is there a civilization on them? In basically 1 generation.
So here's a final thought for you. Imagine HWO finds it. Industrial smog on a planet, say, 10 light years away, and Starshot works. We send a probe, it takes 20 years to arrive, another 10 for the data to get back. We would be in an era where we might know definitively that we have neighbors. We could be watching their industrial revolution unfold from a distance. Cosmic pen pals, separated by a void we can't cross. What does that even do to us? Thanks for diving in with us.